So that's kind of what we want to talk about for solid matter. Now let's talk about a different state. We're going to talk about the gaseous state. And really, how do you go from a solid to a liquid to a gas, these different states of matter? Well, you can change their temperature, volume, pressure, or mass. And what we're going to kind of do is work our way to an equation of state, which is going to be an equation that describes this relationship. So first we have Boyles Law, which says, hey, if I have, say, a container right here, and I hold the temperature of this container constant, then there's going to be an inverse relationship between the pressure and the volume. So kind of as written down here, volume is proportional to 1 over pressure. Now what we can kind of do is say, hey, let me just go ahead and try to squeeze this container right here. Well, what's going to happen as the volume gets smaller and smaller and smaller and smaller and smaller, the pressure inside of it's going to get larger and larger and larger and larger. Kind of conversely, if I were to try to pull this container apart, then the volume is going to get larger and larger and larger and larger, and the pressure is going to get smaller and smaller and smaller and smaller. Now, the next law is going to be relating volume and temperature, and we're going to have to introduce a new temperature scale at this point. It turns out that if we heat an object up, if we increase the temperature, the volume is going to expand proportionally to that. One thing to kind of keep in mind is in the Celsius scale, we have a temperature of 0 degrees Celsius. What this equation here says is, hey, suppose I were to double the temperature, well, the volume should also double. What would happen at 0 degrees Celsius? I try to double 0, and I'm going to get 0. So the Celsius scale doesn't quite work. We need to introduce this new scale, which is going to be called the Kelvin Scale. I'll talk about that on the next slide. Essentially, if we look at the volume versus temperature and kind of extrapolate down, we're going to see that the volume will be equal to 0 at negative 273 degrees Celsius. So this is going to be what's called absolute 0 on this new scale. So that lets us define a new temperature scale, and this is the temperature scale that you always want to work in for any thermodynamics. It's going to be called the Kelvin scale, and essentially it's the same as the Celsius scale, only we've shifted it by 273 degrees. So the temperature in Kelvin is going to be the temperature in Celsius plus 273. One thing you can kind of convince yourself about is a change in temperature in the Kelvin scale is actually going to be the same as the change in temperature in the Celsius scale. If we were to increase by 10 degrees Kelvin, that's also going to be an increase in 10 degrees Celsius. It's just been shifted by 273 degrees, so the change is going to be the same. So any problem where you see a change in temperature, you can actually get away with staying in the Celsius scale, but in general, I would highly recommend always working in the Kelvin scale just to be safe. Now, the last concept for these gas laws is if we have a container with a constant volume, suppose I've got, say, a pressure cooker, and I've got some particles in there, and I go ahead and I heat those, I apply some heat to it, increasing the speed, I'm increasing the temperature of the molecules inside of there, and I'm also increasing the pressure inside of this container because these molecules are running into it at a much larger speed, so the pressure is proportional to the temperature. And we can actually combine these three relationships that we've just talked about into a single equation that says pressure times volume is going to be proportional to temperature. But what about the amount of gas present? We know that density is going to be equal to mass divided by volume, and so volume is going to kind of be proportional to density multiplied by mass. So we can kind of stick a mass right here and say the pressure times the volume is going to be proportional to the mass times the temperature. Now, this is the one time where we won't actually be working with masses that are in, say, kilograms or grams. We'll actually be talking about moles, which you might be familiar with chemistry. Essentially, the number of moles is going to be the mass of an object divided by its molecular mass, which you can essentially look up in a periodic table. So if we were to look up hydrogen, it's going to have a molecular mass of 2 grams per mole. So 1 mole of hydrogen is going to have a mass of 2 grams. Similarly, we could look up elements like neon. Neon's going to have a molecular mass of 20 grams per mole, so 1 mole of it will have a mass of 20 grams. It can get slightly more complicated when we talk about compounds or molecules like CO2. Carbon's going to have a molecular mass of 12, we can look that up. Oxygen is going to have 16. This right here says there's going to be 2 of them, so we kind of can add all these guys together, 12 plus 16 plus 16, and figure out that CO2 has a molecular mass of 44, so 1 mole of it must have a mass of 44 grams. So now we can introduce a very, very, very important equation. It's going to be the ideal gas law, and rather than write the proportionality that we had earlier, we're going to say that the pressure times the volume is going to be equal to the mass in moles multiplied by some constant multiplied by the temperature of the gas. Now, a couple things to keep in mind here is this temperature of the gas must be in Kelvin. This number of moles, that's going to be related to the mass. The pressure and the volume, depending on the units of those, is going to depend on which constant we choose to use. R can have several different flavors, if you will. If our pressure is in pascals and our volume is in cubic meters, then we want to use this one, and this is pretty much the one I'm always going to turn to. If our pressure is in atmospheres and our volume is in liters, then we're going to use this one right here, and this one you'll pretty much never have to see. One thing to be very careful of is with the ideal gas law is make sure you go ahead and you check the units that you're given and make sure that you work in a consistent unit format. You don't want to work with pressure in pascals and volume in liters, for example. And now just kind of some useful facts and definitions. We're going to call standard temperature and pressure, or STP, to be 273 degrees Kelvin or 0 degrees Celsius. And the pressure is going to be just 1 atmosphere, which is going to be 101.3 kilopascals. You could kind of say, well, if I've defined my pressure and I've defined my temperature, now I can relate my volume to the number of moles. So 1 mole of gas is going to have a volume of 22.4 liters at STP. One thing that's kind of useful for the ideal gas law is if the amount of gas does not change, I can say pressure times volume divided by temperature is going to be equal to the number of moles multiplied by that constant R, and that's just going to be equal to a constant. And so if I were to take a gas and say change the temperature, I can say, well, I can write my pressure times volume divided by temperature initially. That's equal to some constant. That's going to be equal to the same constant as the final pressure, the final volume, and final temperature of the gas. Again, it's very important that temperature is in Kelvin and not in Celsius. Something else just to be kind of careful of is that the pressure is going to be an absolute pressure. By that I mean not a gauge pressure. Now suppose just for a second I didn't want to talk about the number of moles in a gas. Suppose I had, say, a chamber right here and it's got some gas in there and it's got, say, 5 molecules. Suppose I wanted to talk about that rather than some weird funky molar mass. Well, it turns out that, a little bit of chemistry here, that the number of molecules in a gas, it's going to be this guy right here, is simply going to be the number of moles, that guy right there, multiplied by Avogadro's number, which is this big honking number right here. What we can then do is we can write the ideal gas law in terms of molecules and Avogadro's number. We could say that the pressure multiplied by the volume is going to now be the number of molecules multiplied by this new constant right here, multiplied by the temperature. This new constant is called Boltzmann's constant, and it's simply the value of R divided by Avogadro's number. And so what this is going to allow us to do is going to write the pressure, volume, and now we're going to have the number of molecules or atoms. And essentially, if you're given a problem where you're given the number of molecules and the number of atoms, this is the form of the ideal gas law that you want to use. I'll just kind of note in passing that this is not the most common. Most of the problems will be using the other ideal gas law. One thing to be careful of is, again, units. This value for R is going to be having the pressure in pascals and the volume in cubic meters, and of course the temperature should always be in Kelvin.